For those of you on this afternoon's or morning's webinar, a little bit of background about myself. I was with Chrysler, Daimler, Chrysler, Fiat, Chrysler for almost 28 years. 20 of those I was in powertrain, focused on engine and transmission, calibration, system performance, fuel economy, diagnostics, drivability. Then I had 2 years where I was responsible for full vehicle reliability planning and testing, durability testing. Then I moved into software quality, and my last 2 years, I focused on cybersecurity, creating a vehicle cybersecurity organization at FCA. I went solo for about a year as an independent consultant, and I'm currently responsible for business development for Argus Cybersecurity, as well as maintaining my consultancy, supporting VFR and their automotive activity. So the intent of this webinar is to give you some information about autonomy and connectivity and cybersecurity and how that development may affect your role in electronics reliability. So when people think about autonomous vehicles, there's a lot of different motivators. It really depends on where you are in life and what you're doing as to what your biggest incentive is. If you work for NHTSA, your motivation is to reduce traffic fatalities. If you are young and party and hardy, it's really cool to have your car be your designated driver. You don't even have to call an Uber if you've had one too many. If you're like me and you've got an hour commute in heavy traffic, it sure would be nice to do something other than drive, so-called driving the car in stop and go traffic. I would much rather be doing something productive or taking a nap or something. And as we age, the aging portion of our population is at risk of losing their freedom and their mobility as their reaction times slow down, their vision becomes impaired, things like that. So there's a lot of interest in providing autonomous vehicles so that the aging population can get around safely. So I talked about traffic safety and fatalities. This chart reflects increases in fatalities and the reason for the fatalities. Starting in 2014 was the first time there was actually an increase in traffic fatalities since this data has been collected. Prior to that, every year, year over year, it was a significant reduction, starting with driver education, seat belts, airbags, things like that, better signage. But unfortunately, with driver distraction and smartphones and texting and things like that, fatalities due to that reason alone are up almost 9%. So autonomous vehicles are one way to take the driver out of the equation. The images on this screen reflect some different concept cars that have been floated out there. There's some people that even envision in a fully autonomous vehicle that they can get rid of the steering wheel. You don't even have to look out any windows. The interior of the vehicle can just be really pretty displays, and you can look out the window for scenery, but not for monitoring traffic. It can just be a portable living room. But as reliability professionals, we know that there's a lot to be done before we are confident enough in the reliability of the vehicle to actually eliminate the driver controls altogether. Vehicle autonomy is categorized in 5 different levels. The original level, what most of us started driving on, were completely driver-controlled vehicles. Your eyes are on the road, your hands are on the steering wheel, you are fully controlling the vehicle. Assisted level of control, these systems are actually in production today. In fact, my Chrysler 200 has adaptive cruise control, which I can set my speed limit. I can set the speed to the speed limit, and if traffic slows down to 2 miles an hour, my car will slow down as well. And when it speeds back up, I will I will follow the car in front of me, almost as if I'm being towed back up to speed. So with my car, when that's engaged, I only have to take care of the steering wheel. I don't have to touch the accelerator or the brake pedal. The next level is partial automation, where you can temporarily take your hands off the wheel. Many of today's advanced technology cars have the technology to do this, but I would say as an industry, we are waiting to give full control until drivers and the market are ready to really handle that, and until the software and the settings are more mature. For instance, my car has lane departure warning and electric power steering. So with the lane departure warning sensors and cameras, the vehicle sees where the lines are on the road, and it will actually on its own adjust the steering angle to keep my car between the lines. I can let go of the steering wheel, and I will see the steering wheel move right to left to keep it centered. Because the system's not mature, and that was the decision that FCA took, if I leave my hands off the wheel too long, there will be an alert on the instrument cluster saying, get your hands back on the wheel. You have a job to do, driver. Stay engaged. But I just wanted to say that to reflect that today, technology today is really through a level 2. There are at least 2 companies coming out with something that some call highway pilot, where the driver does not have to monitor the system at all times. It will actively keep the vehicle between the lanes on the freeway. They're essentially piloting that level of autonomy mostly on the freeway because it doesn't have to take into account pedestrians and dogs and a lot of different traffic situations, traffic lights and stop signs and construction so much. So it's a good way to get the public acclimated to these features, and also to get more time on the road and accumulate higher levels of confidence before they introduce it to more complex driving situations. The next levels above that are high automation, where the driver doesn't even have to look at the road nor touch the steering wheel. And the absolute highest level of automation is full automation, which is where you could take the steering wheel out and the driver could be, the person in the vehicle could be a child. It could be someone that's not even capable of driving. As reliability professionals, we all know that there's a lot that needs to be done before the industry is ready and the population is ready for that type of activity. This slide shows some of the sensors and technologies that are in use in order to provide those features. So to do the adaptive cruise control, long-range radar is employed. For emergency braking, pedestrian detection, and collision avoidance, LiDAR is the primary sensor that provides that functionality. Cameras they detect the lanes, the marking on the roads, and also read traffic signs, as well as providing guidance behind the vehicle for park assistance, making sure that the vehicle is actually parking between the lines in the parking lot. Short and medium range radar is used for cross traffic alert and rear collision warning. So when you're backing out of a parking spot and there's cars on either side of you and you can't see somebody zooming through, those cameras have enough of a wide angle to actually pick up on that and keep you from those types of accidents. And then ultrasound is the technology that's used for park assist. So when it's a really short range, it has that additional precision to help you parallel park or tuck yourself to a parking deck. So when you look at all of this technology in a vehicle, this is what's in production today to deliver the level 1 and level 2 type autonomous features. And as professionals in this area, I think many of us are familiar with the things that can go wrong with each of these technologies. And if there's an issue with one of them, but there's a driver behind the wheel, You can give the driver a message, an alert, and say, hey, pull over. When you get a chance, go to the dealer, turn off your adaptive cruise control, start using your foot. There are actions that the driver can take. The driver, in some ways, is his redundant control system. But when it's an autonomous vehicle, consider what levels of redundancy need to be put in place. And from a system design, the redundancy needs to be separated enough that a failure of that both redundant components or features are unlikely to fail at the same time. So they need to be separated by distance, by circuit, by exposure to the elements, and things like that. I know some of the things I'm bringing up may or may not touch you in your daily life, but I want you to be aware of these types of thoughts and concerns, because I'm guessing in your role that you're part of the community that is designing the system and is taking and is thinking about the architecture and faulted reactions and driver warnings and things like that. So as a member of that community, it's important to make sure that your peers are aware of these considerations. When we talk about image detection, you know, we know as drivers what a stop sign looks like. We know what traffic lights look like. But if the software is only as good as it is programmed to be, and so if the camera system sees a red light and a green light and both seem to be pointed toward the car, which one wins when there's a conflict? Well, in general, the general practice is if there's a conflict, the vehicle stops, because that's the only safe thing. You don't want it to cross the intersection and be hit. So if that happens, then now the rest of the traffic behind that car doesn't expect it to stop, and now it's at risk of being rear-ended, and more annoying and less of a safety risk. Now traffic has to try to get around that car that's unusually parked. And how do you clear that condition? If the driver's not paying attention, you know, how do you car moving again? The stop sign that's at an angle because it was hit, if that was a street sign and it was twisted, how does a car know which road is which direction? And my favorite, the sign that says entrance only, do not enter. What does the car do with such conflicting information? You know, in this instance, it would probably just not enter because that's the safer path to take. But if you're in the car and that's your destination, you're going to be really frustrated that the car won't go there. Other things that an autonomous system has to take into account is spontaneous actions. So in this instance, the road was flooded, it was closed. And you know, if it's Heinz Drive in Detroit, you actually know how long it'll take till the flood subsides. In this case, maybe a power line was down or some other, you know, something was washed out and they had to repair the road. But the car only knows the road information that it gets from the cloud or what it was preloaded with when it was last updated. So when there's spontaneous changes in the traffic, and here it's cones marking it and not lines, so the car is going to stay to the edge of the cone. So what about this cone that's in between? Does it go to the right? Probably, because it can't go over the curb. So anything that would confuse you as a driver, imagine that your control system is at risk of being confused as well. And all of these use cases, when taken one at a time, are solvable. You can look at it, you can learn more about the situation, you can integrate that. The challenge is there are so many use cases like this. But people working on such systems have to take all of these into account. So you can just imagine how many lines of code and how many different branches there are in the software. And if they miss one, what's the default reaction of the vehicle? Other things to consider, I mentioned earlier about redundant sensors and thinking about how they're isolated or from an environmental perspective. So the cameras on these vehicles that are driving in the middle of a blizzard, the cameras could get obscured by the snow. So should the car companies put duplicate sets of cameras How do you decide where to put the other one where it's not going to be obscured? The view is going to be different. The input into the computer is going to be different. Dust, so not just snow obscures it, and maybe with snow you could have some sort of a wiping mechanism to clean it. What do you do with dust? You try to wipe dust off, and you're likely to scratch the camera lens. Sun, you can't wipe sun off. And if you put some sort of a, transitioned type lenses on your camera screen, now that's one more thing to worry about from a reliability perspective. The next aspect, so cameras can pick up on the lines in the road, but the guidance is actually primarily guided by the map database that's in the system. Map databases are probably the single biggest file in the head unit in the vehicle. There's many gigabytes of information about the road system. Now consider between 2000 and 2013, there were almost 14,000 new miles of roads created per year in that timeline. And another 31,000 roads were widened. So if the autonomous vehicle is designed to track along a certain coordinate and the coordinates change, the car is going to be in the wrong place. There are a lot of over-the-air updates of content in the vehicle, but like I said, map files are very, very big, and most people don't necessarily want to pay for those updates through their data plan. It also, because it's so big, it takes a long time to upload. So the current approach is most manufacturers provide updates every 6 months to a year. And in some instances, the customer has to go to a dealer to have that done, or they have to do it with a USB stick plugging into their radio head unit. So some may not do that, in which case their maps will be out of date. If you're like me, 64% of new roads are in residential neighborhoods. So if I'm going to a friend's house, or I just bought a new home, or I'm buying a home and I'm going to look at a bunch of new houses, how am I going to get there if the autonomous vehicle doesn't have the address to even navigate to, or have it in your system? I talked about updating software over the air and app data. Autonomous vehicles rely on or benefit from connectivity. They also pick up on traffic lights changing and things like that. This map here shows is an illustration of cellular reception. So got a lot of cell phone towers in the Northeast, South, and Midwest. In California for sure, Washington, Oregon, but there's a lot of non-covered areas in the West and Central U.S. A lot of us like to take driving trips, beautiful scenery. So does that mean you have your autonomous car for where you live, but you want to go on vacation, you have to drive the old-fashioned way? Will people still even know how to drive? Lots of different cultural questions for us. So another benefit of the cloud, and I guess, if you're in a metropolitan area, you do have reception, so you are likely to get the traffic information sent to your car so that it can avoid this traffic accident and avoid these red congested roads that can keep you smooth sailing on the green, less traveled routes. But as a reliability professional, you need to consider what happens if this data is not coming through. What happens if it's corrupted? What about if it's intermittent? Things like that. Where is this information stored? What are the electronics devices in the vehicle that allow that data to be communicated to the car and then used by the appropriate modules. That's really how this affects you. Other things for consideration, I know when I'm driving or merging onto a freeway or somebody else is merging in with me, I make eye contact with the other driver, and there's either a head nod or a hand wave to let them know it's okay to get in. What will the computer systems do? How will we keep it from misinterpreting someone wiping their hair out of their eyes as a hand gesture to go on ahead and merge in front of me? Remembering that one of our objectives of autonomy is to help with traffic congestion and give us more free time. If cars are moving slower because they're confused or they're getting mixed signals, that can back up traffic even more. When there is an accident on the road, it's a very spontaneous thing. How will the autonomous vehicles know where to go in this instance? What kind of hand gestures will be given by any of these professionals on the ground that are taking care of this accident? You look at the higher concentration of dots, I'm guessing it's like a carpool lane. How will the autonomous vehicle know that they need to stay in this one in the second lane from the right instead of going all the way to the open one? I'd personally want to go in the open one, but no one else is there. What's the car going to do? What as engineers, what should they program the car to do? So with all those challenges, a lot of people in the autonomous vehicle activity are increasing their testing ability. So the pictures here on this slide reflect M-City, the University of Michigan, Ann Arbor closed course for autonomous vehicle testing. They've got traffic circles, lots of different lanes, curves, straightaway, parking pads, simulated cities, parallel parking, street lights, traffic signs. So they try to simulate as much as possible so that on the closed course, automakers and suppliers can get reliability data and experience in all those different situations. There's another course being built at Willow Run. The Willow Run Airport is being converted into an autonomous vehicle test grounds. And I believe that there are other courses being built around the US and elsewhere. My finger slipped. Sorry about that. So if I'm guessing your backgrounds, probably most of the reliability type activity you work with are more the failures that are a result of thermal overload, fatigue, issues with circuit boards, system issues. You may or may not be thinking about mud or snow obscuring a camera and what that does to the system function. Having come from powertrain, I spent a lot of time thinking about what the fail-safe mode was of the vehicle or what the faulted reaction was. So for instance, throttle position sensors have redundant contacts. So if one of the contacts is corrupt in some way, the other one is used, but the system knows that the redundancy is no longer there, and the customer is alerted that there is an issue that needs to be resolved. And the concept is they have time to get to a dealer to have that sensor replaced before the single remaining contact may be no longer capable of giving a reliable signal. So when you think about autonomy and you think about all those sensors and images that I showed several slides ago, what is the strategy? What's the system strategy for that? What kind of redundancy makes sense? What's the best way to give, to make the vehicle still usable, even when the system is compromised in some way? You know, if you or I were in a vehicle and a sensor was covered with snow, we don't want it to just stop in the middle lane of the freeway. We also don't want it to just pull over to the shoulder of the freeway and sit there. We'd really like to be able to get home or get to a dealership or somewhere where we're not stuck in the car. So that's what I mean by maximum vehicle capability. And I mentioned earlier that I've been spending the last 3 years of my career focused on cybersecurity. And I talk about systems being compromised. They can be compromised through a thermal issue, or they can be compromised by a hacker. What is that customer messaging? You don't want to panic the customer. You don't want them to have them freak out. On the other hand, you want them to be motivated to actually go to a dealership and get their system, have the issue be addressed. So just a little bit about cybersecurity and hacking threats. Many vehicles today are connected. There is an embedded modem in the vehicle. If your car is capable of calling 911 on its own, if you're capable of having cloud information streamed to the vehicle, that's essentially an internet connection to your car. And if the internet's connected, hackers, if there is a vulnerability, hackers would have a way into your car. What do hackers do with cars? Well, there haven't been any public threats. What's been demonstrated so far is several researchers have demonstrated what they can do. So let's say that there are people that they call themselves hacktivists, and they believe it's their responsibility to inspire the automotive industry to move very quickly and protect cars from cyber threats. So some of the things that they have demonstrated is spoofing messages. They pretend to be the legitimate module, and they send a command that is either at the wrong time, like turn the steering wheel to full lock at 80 miles an hour, or with an inappropriate value, like go to 100 miles an hour instead of 10 miles an hour. They can also overwhelm the bus by sending a bunch of junk, and that can actually result in inhibiting safety critical messages. Like the brake module never sees that the brake pedal was pushed because it was just overwhelmed with a bunch of traffic. I'm not telling you this to scare you, but to let you know the importance of system reliability thinking and thinking about the full vehicle functionality and how your part plays into the whole. So access to the CAN bus and connectivity can take different forms. I talked about the integrated modem. Other ways that vehicles can be connected to the internet include connected dongles or devices that are connected to the OBD port. Insurance providers are offering dongles to give their customers safe driver discounts. These dongles are connected so that they can transmit the data back to the insurance company, and the insurance company is monitoring how fast the car is going, what the braking behavior is, and steering behavior is. So if they're monitoring that, it means that they're accessing those safety critical buses. There are other there's OEMs that provide vehicle connectivity through something called tethering, which is the act of having a smartphone connected via Bluetooth and providing internet access to the car that way. Not all Bluetooth connections provide internet, but many do. And then the last connection type is the USB port. USB devices are not, there's no standard security that is implemented in them. So if a criminal wanted to do a very large exploit, they could corrupt several USB sticks and give them away as free music at a concert or some other giveaway at a sports stadium or something like that. And many people naively would plug those into their car to play the music. And that would be a mechanism for them to get their virus or their attack into those cars. So a lot of this I'm telling you as a public service announcement to help you become aware of some of those threats so that we all can start changing our behavior and lowering our collective risk. So a few things that system developers should think about. Not to be an alarmist or a scare, to be too much of a fear monger, but most security professionals, most if not all, believe the best way to act is as if your system will eventually be hacked, and to take every precaution necessary. Think about how you could anticipate what the criminal hacker might do. Think about how you might detect it. So from a cybersecurity perspective, the first thing is to prevent. If your prevention is not sufficient, then you want to detect. And then you want to think about how the vehicle reacts, what kind of fail-safe modes should be employed if the vehicle is compromised. When you're doing your system FEMA, your cybersecurity as you go up and down the V, and what you would do differently. Talked about preparing plans for loss of function, interfacing systems. So it's one thing if you lose your own primary function, but if you're relying on other systems or information from other modules to do your function, think about what happens if they are compromised, not just you. Think about how quickly you can develop improvements. Are you organizationally set up to react quickly? And how do you get those updates? How do you get that new software into existing vehicles? So Argus Cybersecurity has an intrusion detection software and over-the-air remote monitoring so that they can provide updated security profiles into existing vehicles. From your perspective, assuming you work on electric, think about isolating safety critical systems. If there is risk of a thermal overload in one area of the board or cracking or something like that, obviously you want to, let me put it this way, you're going to design against that. So from a board layout, try to have your redundancy separated so that if something is missed, perhaps it's a misbuild, some product quality issue during the build, that an issue in one area won't affect your redundant sensors. So from a cybersecurity perspective, we recommend having all the cyber calculations on a dedicated micro that is not the same micro that's controlling the vehicle functions. And from a connectivity perspective, we recommend isolating the connectivity functions from the safety critical functions as well. There will be some access through the CAN bus, but you'd rather not have them physically on the same chip or on the same board. So that is the extent of my presentation.
And thank you everyone for attending. Have a great day.
Thanks, Mark. Thanks everybody for listening.